Okay, so welcome back. Our stopping point last time was right before our description of these hyperbolic lines, right, or these non-Euclidean lines. I guess I haven't called them hyperbolic technically yet. I've just been calling them non-Euclidean. So recall that last time we had discussed um, our transformations we were going to use in the sense of Klein to determine what kind of geometry was going to result on the upper half plane. And so this type, first of all, to remind you of what these transformations looked like. So they looked exactly. So the extensions that we looked at from the fractional linear transformations of RP1 to upper half plane, the horizontal translations and dilations when the dilation factor is positive extend in the obvious way, and they look exactly like you think they might look. The reflection of the y-axis looks slightly different, of course. So instead of uh, at least algebraically, it looks different, right? So z gets sent to minus its complex conjugate. So what this looked like was the following. So point here in upper half plane, z, x plus iy, gets sent to minus z bar, which is minus x plus iy, right, which is exactly this reflection that we wanted. And then the other thing was inversion in the unit circle looked like this. Right, so in RP1, x gets sent to 1 over x, right? So in this particular example where x is bigger than 1, this is what it looks like. You can't tell that that's inversion in the unit circle in RP1 because there's not enough room. When you move to the upper half plane, the thing that this should be is inversion in the unit circle. And so z gets sent to 1 over z bar, which sends a point written in polar form, r times cosine theta plus I sine theta. This goes to 1 over r cosine theta plus I sine theta. And so it's inverted in unit circle in this way. And again, this is in the case that you have complex number z where r is bigger than 1. Okay, so we have our transformations. These are the Möbius transformations. And then, as I said before, the reason why this comes at the end is so that we can ask this question, like what kind of geometry results from taking these as our transformations, right? What are the things that are kept invariant? And it turns out that you get a geometry that satisfies all of Euclid's postulates except the parallel postulate. Okay. All right. And so anyway, taking these Möbius transformations as our transformation group or group of isometries for the geometry that we want to study for the upper half plane, we want to see what results from that. So the idea here is I want to see what the equations for non-Euclidean lines look like. Right. So up till now, I've just given you, what these things are, but I didn't actually show why they work out that way. So I explained to you what the lines were in the upper half plane, right? They were either vertical lines or they were halves of, they were semicircles that were centered on the x-axis, right? Which is our boundary line RP1 in the upper half plane. Okay, so first, consider the lines that are actually Euclidean lines. All right. So I claim that, of course, these are the vertical lines, right? So quick review, right? My lines I'm claiming in the upper half plane are either vertical lines or semicircles, right? So drew a picture of this previously. So here was the picture, right? So lines either were semicircle centered on the x-axis or were vertical lines. Okay. All right, and so the lines that are actually Euclidean lines look like this, right? X equals a for some real number a. Okay, so this is what they look like. So then some arbitrary point in the upper half plane on this line is z is equal to a plus iy, right? So it has real part a since it lies on that line. Okay, thus z bar is a minus iy. Okay, thus z satisfies the equation z plus z bar is equal to 2a. Okay. Well, just add these together, right? Add these together. Z plus z bar is 2a. Okay. Now, of course, going backwards, looking at lines or points that satisfy this this equation, and seeing where those points would lie. Well, again, you get the same thing. So point Z in the upper half plane satisfying this equation lies on the vertical line x equals a, and vice versa. Any point on x equals a is some point in the upper half plane satisfying this equation. Okay, so this really is the equation for that line. Okay, and so complex conjugation gives us a way of writing very simple equations for these objects. Okay, and we're going to mimic this for our other lines. So now consider what I've called lines, right? So consider the lines that are semicircles with centers on the x-axis. Okay. All right. Well, if C is the center, right? So that's just some real number, and R is the radius. Then any Z on the semicircle satisfies that the length of Z minus C is R, right? Or another way of thinking about this is that the distance from Z to C is R, okay? Or equivalently, the length of Z minus C squared is R squared, right? Whenever you deal with length things, it's often a lot more convenient to deal with the square of the thing rather than the length itself. Okay. But these we can make a little nicer. Right? We can make these nicer because these don't tell us as much in this form. All right. So let's do exactly that. Okay, note that for any complex number, so for any complex number x plus iy, we have that the length of x plus iy squared is x squared plus y squared, right? Which, of course, we can write as x plus iy times x minus iy, which, of course, is the complex number x plus iy times its conjugate, x plus iy bar. Right? Thus, the length of z minus c squared is z minus c times z minus c bar. Complex conjugation is a linear thing, so this is z minus c times z bar minus c bar. But c bar is a real number, right? So this c bar is just c. Okay, thus the equation z minus c squared is equal to r squared becomes z minus c times z bar minus c bar is equal to r squared. Okay. Now if we expand this, and we're still pretending like this isn't a real number yet, so if we expand this, what do we get here? We get z times z bar minus c times z bar, right, minus c bar times z, right, plus c bar, and that's equal to r squared. But c bar is equal to c since c is real, right? It has zero as its imaginary part, so c bar is the same as c. All right, so simplifying this, what do I get? I get z times z bar minus c times z plus z bar plus c squared minus r squared is equal to 0. Okay. So this is an equation for this line, right, in the upper half plane. Now, combining that with this, I'll label this 1, and I'll label this 2, right? So I have an equation describing the vertical line, right? That is one of our lines in Euclidean, or in this non-Euclidean upper half plane. And I have this second equation, which looks different, but both of these are actually equations of a particular form. So note both 1 and 2 are equations of the form a times z bar plus b times z plus z bar plus c is equal to 0. Okay, for big A, big B, and big C and R. Okay, and you can see that. So in this case, it's obvious what each of these things are. In the first case, big A was 0, and big C was minus 2A, and B was 1. Right? Okay. Okay. All right. Also, note that if A and B are not both 0, then this form reduces to either 1 or 2. Okay. Okay. Meaning that as long as both A or B are not 0, then you actually get an equation that is either an equation for a vertical line or an equation of a semicircle. So, for instance, let's say that A was 0, right, but B wasn't. Then what I get is what I'm going to get is an equation for a vertical line. Okay. So the thing I would get 2A would be minus C over B, right, in that case. If B is 0, but A is not, then what I would get was the equation for a line that has center 0, for instance, in that case. So if A is not 0, in general, I can what I would get is my little c, my center, is going to be minus B over A, for instance, after I divide through by A. Okay. All right. So as long as both A and B are not 0, they reduce to either case 1 or case 2 in terms of these lines. And so this is the form of these lines, right? So rewriting that. Thus, equations of non-Euclidean lines, I'll still put them in quotation marks, are the equations of the form A z bar plus B z plus z bar plus C is equal to 0, where A, B, and C, which are real numbers, are not all 0. Okay. All right, so here's what my equations of these lines look like. Now, what's the, why do I need to talk about this? Well, if I'm going to try to understand what these transformations do to these things I'm calling lines, then the easiest way to do that is to come up with some form, right? Some equation that these lines always have to take. And that way I can actually see algebraically what these transformations do to these equations so that I can see, oh, do they preserve them, right? Do they send lines to lines? Do they send lines to something else, right? That's the idea. Okay. All right. Okay. And so now what do I want to do in order to see? So my goal is to understand the geometry of the upper half plane that arises from taking the group of Möbius transformations, right, which are these extensions AZ plus B over CZ plus D, right, where A, B, C, and D satisfy exactly what you think. I'm not going to write that out here, as my group of transformations. for the geometry of the upper half plane. All right, so this is my goal. All right. Well, what is the idea here behind, like, what's the kind of the first step, I should say? So what is kind of a first step here is really understanding what these Möbius transformations are doing. Okay. The first way that the Möbius transformations arose actually was not exactly in the way that we did them. So the way they originally arose came from this was done by the person, they're named after Möbius. So the original idea behind the Möbius transformations were that they were introduced as being a generalization of reflection groups, or like the just thinking about normal reflections as an isometry of the plane, and the idea was generalizing it in a way that rather than thinking of just ordinary reflections, it was reflection in the unit circle. Okay, was the idea. And so the idea that Möbius had was to come up with a theory of transformations that were generated by reflections in circles, generalizing from reflections in the unit circle. And it turns out that all the Möbius transformations, the half plane, are the product of those reflections. So this has that analogy with what we did earlier. You know, we had like the three reflections theorem that said that any isometry of the plane was actually a product of up to three reflections, right? So Möbius's idea: study transformations that arise as products of reflections in circles, generalized from reflections in unit circle. Okay. And so it turns out that these transformations, so transformations that arise as products of reflections in circles, those are Möbius transformations. It turns out that all of the Möbius transformations arise in this way. Or said another way, any Möbius transformation can be thought of as a product of reflections in circles. Okay. All right. Okay. So let's first define reflection in arbitrary circle. Okay. And so idea, right, reflection in an arbitrary circle. Now, what was easy about doing reflection in the unit circle was that since every complex number has polar form, once you saw how this worked, right, you're literally just taking the r that comes from the polar form and sending it to 1 over r instead. Okay, and so that was the idea. But here, you know, we can't just do that. But what we can do is actually mimic kind of so we want to mimic what it is that happens in that picture, right? So when we drew that picture, which I still have over here, what we want is, rather than this thing being, you know, specifically z and 1 over z bar, is that I have some radius now. Instead of 1, I would have generic radius r. And instead of having z and z bar here, I would have a point I call q, or maybe I started here even, right? There's no reason to specify what direction is going on here. But if this is my point q, then this point would be, say, q prime. Okay. Now, it's not exactly going to be of this form because we're not reflecting in a unit circle. We're reflecting in a circle of some general radius r. Okay. But the idea, of course, is also that, this circle that we're talking about might not be centered at the origin. So instead of origin here, I could just have a point P. Okay. So I want to mimic this picture where I've replaced these things, right? You can cover up these things that I've written here. And this is the picture that I want. Okay. All right. So how do I get that? Well, we say that points Q and Q prime are reflections of each other in a circle with center P and radius r if, so the thing we're defining is reflections of each other in a circle with center P and radius r. If P, Q, and Q prime lie in a straight line, all right, so those 3 points are collinear. Just to remind you, this is the picture I wanted to have here, and that's clearly true in that picture. So they lie in a straight line, and what is kind of the key defining thing? Well, it's that the length of PQ times the length of PQ prime is r squared. Okay. Now, looking at this at first sight, this might seem a little strange, but if we go back to this picture, what is going to be the analog here? Well, the analog here would be length of PQ. RP is O, the origin. So this would actually be length of Z times length of 1 over Z bar, in this case, is equal to 1, right? That would be the thing that's being stated here. Okay. And you can go back and check that that's actually the case. Okay. All right. And so this is my definition. Okay, this is my definition of reflection in an arbitrary circle. All right. Okay. Now let's see what is going on here with respect to these reflections and these transformations that we extended to the upper half plane, right? Okay. And so, if the circle, or its upper half, right, the upper semicircle, is a non-Euclidean line, then its center, P, lies on the x-axis. And reflection in this circle can be composed from generating transformations of the upper half plane. So, and reflections in this circle can be composed of generating transformations So remember, we have a list of these. The generating transformations of the upper half plane. Okay. So first of all, let's remind ourselves what the generating transformations are, and then we'll see how this is done. So my list of generating transformations, if I can dig it out of my pile of notes here. Okay. Here's my list of generating transformations. There's horizontal translations, the dilations where k is positive, reflection the y-axis, and reflection the unit circle. So this is all we need. So these generate all things that look like this, which we're calling Möbius transformations. All right. So to see how we can get reflections in the circle generated as some generating transformations from that list, what would I do here? Well, it might already be obvious what to do here. If I have a circle that lies on a non-Euclidean line, then I'm in this case, right, where actually my center is on the line RP1, right? It's on the x-axis, but it's not at the origin. It's at some point P. And so what would I do to really line it up with this picture? I would just move P to the origin. Right? So I move P to the origin. And I can do that with a translation. Right? So again, here's my list of generating transformations. I can translate. Right? I'm translating on the x-axis now. This is no problem. So first step, translate P to the origin. Okay. Now what? Again, I am trying to line up a generic picture with the radius 1 picture. So now I've taken this and I've mapped it to the origin. But this radius that I have, I want it to be 1, but it's actually just some generic r. How do I make it 1? Well, again, my generating transformations, I have dilations, and I can dilate that radius by a scale factor of 1 over r, which is definitely positive. Okay, so I can reduce the radius to 1 by dilating by a factor of 1 over r. Now I have a circle centered at the origin of radius 1. I have unit circle. So now I can reflect in unit circle. Now I have to move everything back. Right? So next, if I'm working in reverse order here, next I restore the radius to r by dilating by r. And lastly, I translate the center back to P. Okay. And so translation in an arbitrary circle that is part of a non-Euclidean line, right, is just easily seen to be generated from these generating transformations for the upper half plane. Okay. Okay. Now, what if I consider reflection in an arbitrary vertical line? Why would I be considering this? Well, what we just did was the case of my non-Euclidean line being a semicircle, right? The other option is my non-Euclidean line is actually a vertical Euclidean line, x equals a. All right. So then how can I make this reflection across the line x equals a be generated from those transformations of the upper half plane? So this is also generated by our generating transformations of the upper half plane. So to see that, what do I do? So first, translate x equals a to the y-axis. Similar approach as before. Then I reflect in the y-axis. How do I do that? This is my reflection. Z gets mapped to minus its complex conjugate, right? And then I translate the y-axis to x equals a. And that's it. Right. So what did we show with these two considerations we made, right? So first, reflection in a non-Euclidean line that is a semicircle is actually generated by these transformations of the upper half plane. And similarly, reflecting in a non-Euclidean line, that's the only other way that a non-Euclidean line can look, which is when it's a vertical line. This can also be viewed as being generated by those generating transformations for the upper half plane. Thus, all reflections in non-Euclidean lines so all reflections in non-Euclidean lines are products of generating transformations of the half plane. Okay. Okay. Next, we show that conversely, every generating transformation in the half plane is a product of reflections. So conversely, we show now that every generating transformation of the upper half plane is a product of reflections. And thus, so is every transformation of the upper half plane. So since it's true for all the generating transformations, and since any generic transformation of the upper half plane is generated by those generating transformations, then it's true for any arbitrary transformation of the upper half plane. Okay, so how do we show this? We want to show now that every generating transformation of the upper half plane is a product of reflections. Two of them are easy, right? So first, the two generating transformations, z getting sent to minus z bar, and z getting sent to 1 over z bar, are reflections by definition, right? So I only need to consider the other two. So I only need consider the other two. Okay, well, the other two were translations and dilations with positive scale factor, right? So the horizontal translations right, to check here. So I'm sending Z to Z plus L. How is that a reflection? Well, this is actually a Euclidean translation. But we know that a Euclidean translation is a product of two reflections. Thus, it is a reflection, or I should say a product of reflections in the lines 0, x equals 0, and x equals L over 2. You had a homework assignment doing this back in chapter 3. Okay, so horizontal translations, those are checked off. That's a product of reflection. So then the only other thing is dilation with positive scale factor. So dilations that look like this. So Z gets sent to KZ, where K is positive. How can I view this as a product of reflections? Well, this is the product of the reflection. So this is the product of the map that sends Z to 1 over Z bar. That is reflection of the unit circle. And the map that sends Z to K over Z bar. Right. Which is reflection. So this is reflection in the circle with center O. And radius square root of K. Okay, so viewing this as being composed of these two reflections, or the product of these two reflections, is our last, this is the last thing we have to show. Okay. Okay. All right. And so, one more thing to note here. So note, so first of all, let me say what it is that we've actually shown again. So first, we showed that all reflections in non-Euclidean lines are products of generating transformations of the upper half plane. And conversely, every generating transformation in the upper half plane is a product of reflections. And thus, so is every transformation in the upper half plane. Remember that we wrote our transformation of the upper half plane in this form that I had written previously. Okay. And so what this says is that what are these? These are exactly products of reflections in general. So these are actually what these things are. These Möbius transformations are products of reflections, where the reflections that we're talking about can be reflections in arbitrary circles. Right? We actually showed that that all these generating transformations were actually all versions of reflections. And so restricting your attention to studying transformations of the upper half plane that arise as products of reflections in arbitrary circles, that's actually the same. This is actually the same thing as starting from our notion of extending these and calling those the transformations of the upper half plane. So it doesn't matter what approach you would use, you're studying the same objects. Okay, so note ordinary reflection. So ordinary reflection, i.e. reflection in a straight line, so this is the limiting case of reflection in a circle obtained by letting P and R go to infinity. And the way that we want P and R to go to infinity is that the circle goes to a straight line, right? In a way that the circle goes to a straight line. Okay. Remember, so since Euclidean lines are the fixed point sets of ordinary reflections, right? Right. Another way of thinking about a Euclidean line is viewing it as the collection of fixed points for some given reflection across a line, right? That line will be obtained in that way. So Euclidean lines are the fixed point sets of ordinary reflections. It is nice that our lines in the upper half plane are also fixed point sets. Of its reflections. Right, since what we're calling reflections here, right, have been slightly generalized to include reflections in a circle. Okay. Okay. So I think that's all I wanted to say for today. I believe we have a good. So by the end of this week, we'll have basically finished the chapter, which will leave us like an extra day of talking about stuff. I have some videos, some YouTube videos I'm going to link to you to have you watch. They're only a couple minutes long, each of them, because they're really, really good. They were made, at least one of them was made like many, many years ago, but it's actually still one of the best videos for describing Möbius transformations. It's a nice way of thinking about these things. Anyway, so that's that. I will post your last homework before Wednesday, and it'll be due. It'll be due like we'll say last day of classes. I'll have it due next Tuesday, and it won't be too long, and it'll be just tidying up some of the stuff that we did in Chapter 8 with these with the geometry of the upper half plane. But anyway, I will.